Hello, everyone. So welcome to this next lecture, which is the first lecture to cover Chapter 2, Algorithms with Numbers. So what we're going to start to do in the last lecture or last week, you recall that we were talking about how things like addition or actually another one is multiplication. We need to be a little bit more careful about how many computer steps or how many operations it takes to perform them. And so in this chapter of the course, we're really going to go through several of these basic operations and determine efficient algorithms for solving these problems. So typically we're going to be dealing with large binary numbers and performing operations like addition, multiplication, then we're going to do exponentiation and some other operations. And the motivation for this is that there's two important problems that occur frequently with numbers. The first one is factoring. And so that's given a number, n, express it as a product of prime factors. So if the number is prime, then its only factors are 1 and the number itself. And if it's a composite number, then it has other factors, right? And then primality is given a number n, determine whether it is prime. It turns out that factoring is hard. As far as we know, there is no algorithm that solves factoring in a polynomial time in the number of bits of the input number. So the fastest known algorithm is exponential in the number of bits in the number n that we input. On the other hand, primality, testing if a number is prime, can be solved efficiently. And so even though these two problems are very linked, they seem almost the same, right? I mean, certainly if we had an algorithm for factoring, we could solve primality. But with an algorithm for primality, we can't solve factoring, at least as far as we know. And secure communication relies on this kind of duality, that it's easy to do one of these things and hard to do the other. And so in this chapter, we're going to build up all the basic algorithms. And at the end of it, we'll be able to present RSA cryptography, which is an application of algorithms with numbers. And so you're going to have to hold tight a little bit as we develop a bunch of core algorithms. And then at the end, we'll kind of put them all together to show how RSA cryptography works. So let's begin at the start and consider addition. Addition, there is nothing fancy here. The way you do addition with large binary numbers is exactly like the grade school kind of algorithm for addition. So as an example, let's suppose I'm trying to add two binary numbers. One of them is 1, 1, 0, 0, 1, and the other is 0, 1, 1, 1, 0. So this first number is 25, and the second number is 14. So to add them, you just add the column and then you carry if you get a number that's not a 0 or a 1. So when we add these, we get a 1, a 1, a 1. Here you get 1 plus 1 is 2. So you carry, right? So then this becomes a 0 and we have a carry digit, which is a 1. Again, you add 1 and 1. That makes in binary 1, 0. So you write a 0 here, and we have one more carry here, and then you get a 1. Right? And these up here are our carries. And so the final number here is 32 plus 7. It's 39, which of course is the correct sum. So what is the runtime of this algorithm? We're going to be considering runtimes in terms of the number of bits needed to represent each number. So just like, I mean, I think that sounds very clear, but just to be very clear about like what I mean by that, this number is 25, but it only takes 5 bits to represent it. And so the runtime, we want to characterize it in terms of 5, the number of bits, not 25, the value encoded in those bits, right? So the runtime of this algorithm is, first thing we have to think of is how, if you have two n-bit numbers, how many bits can their sum be? Well, at most n plus 1 bits, right? So So the sum of x and y can be at most n+1 bits long. And each bit can be summed in constant time. So each bit in the resulting number x plus y can be calculated in constant time. And since you have to do n+1 of them, the runtime we get is big O of n. So in general, addition scales linearly with the number of bits in the input numbers. There is something like in a computer, you typically have an ALU, which performs in hardware certain additions, like either 32 or 64-bit additions. And so often this kind of speeds things up a bit, but this is still just some constant. And if you start to add very large numbers, the runtime is going to be big O of n. Okay, let's move on. So we've now, addition is big O of n, where n is the number of bits in the input numbers. What about multiplication? We'll visit this a few times. It turns out already multiplication of n-bit numbers is not, it's not immediately clear what the most efficient algorithm is. So let's begin with this algorithm. It's going to follow from kind of a rule that says the following. If I'm multiplying x and y, that's the same as multiplying x times the floor of y over 2, in the case where y is even, multiplied by 2, or the floor x multiplying the floor of y over 2 times 2 plus another x if y is odd. Okay, why? You might be wondering why on earth I'm writing it like this. First of all, you notice that if y is even, so this thing just equals y over 2 if y is even. Right? And so then this makes sense, right? 2 times x times y over 2 is just going to be x times y. And so the first row makes sense. On the other hand, if y is odd, if y is odd, then the floor of y over 2 is going to be missing one x. And so then we add the extra x on. So let me give you an example of each just to show you what it is I'm saying. So let's say that we're considering x is 8, x is 12, let's say, and y is 8. In that case, then y is even. And so the floor of y over 2 equals 4, right? Y over 2 is 4, and then the floor of 4 is 4, right? The floor is the largest integer that's smaller than its argument. And so we get that 12 times 8 can equivalently be written as 12 times 2 times, it can be equivalently written as 2 times 12 times 4. And in the other case, of course, this then is correct, right? It's just 96. And then in the case where if, on the other hand, y is equal to 7, which is odd, then the floor of y over 2 is going to be the floor of 7 over 2. Right? 7 over 2 is 3.5. So the largest integer smaller than 3.5 is 3. Equals 3. And so the result would say 12 times 7 is equal to, writing it here, right? 12 plus 2 multiplying x, which is 12, multiplying the floor of y over 2, which is 3. And so if you look, this is 12 times 7 because you get 2 times 12 times 3, which is 12 times 6, plus another 12. That's 7 12s, which is the right result. Okay, so why on earth am I writing things like this? Well, the reason is that floored division and floored division by 2 and multiplication by 2 are straightforward operations in binary. In particular, multiplication by 2 is just a left bit shift. So as an example, if I have, let's say y is a number which is 1, 1, 0, 1, 1 in binary. So I'm writing this little lowercase 2 to denote that that's a binary number. Then this is in decimal, this is 27. Then 2y is just equal to 1, 1, 0, 1, 1, 0. Which is 54. Right, so I just added a 0 at the end. Floored division is just a right bit shift. Floored division by 2. So taking the same example, let's say that we have y is equal to 1, 1, 0, 1, 1. Then the floor of y over 2 is just a right bit shift, which is just then going to be 1, 0, 1, 1, 0, 1. Right? We just drop the last bit. And so this again is 27 here. And this then floored division is going to be 13. Right, so I should write my little subscript 2. So that then gives us an algorithm for performing multiplication. It takes in 2 binary numbers, x and y, that are each n-bit integers, and it outputs their product in binary. And the way it works is it's going to be a recursive algorithm again. And if y is 0, then the product of x and y is also 0. So we just return 0. That's our base case. Otherwise, we do the following. We calculate x multiplying y over 2. Right? That's just this, what's in the brackets in this rule, x multiplying the floor of y over 2. And then if y is even, we just multiply that by 2. Right? That's now exactly this first row, 2 multiplying what's in the brackets. And otherwise, we are going to return 2 times that quantity, what's in the brackets, plus an x. 2 times what's in the brackets, plus an x. And since these are just bit shifts here, right? This operation is just a bit shift, and this operation is a bit shift. This one's a bit shift, and then we have an addition. We're like kind of using very basic operations to implement multiply. So it's kind of a cool algorithm. I mean, it seems, when I write the rule, it seems unusual, but now you kind of see I'm able to implement it in a very simple manner, right? Very few lines of code. So correctness, I mean, I'm just directly implementing the rule in a recursive fashion. So I'm going to say that it's correct, directly. What about complexity or runtime? So let's think about what's going on. If you notice, right, we're always shrinking the second argument in multiply, right? We start off with x multiplying y. The next time we call multiply, it's x multiplying the floor of y over 2. And it finally terminates when this second argument shrinks to be a 0-bit number, right? There's nothing left in it, or it's just a 0. And at that point, we return our base case. So how many times will we call multiply? That's the first thing to think about. Well, we talked about the fact that floored division by 2 is a right bit shift. So each time we do a floored division, we lose 1 bit in the second argument. Since it started off as an n-bit number, that means that it'll take us n recursive calls before the second argument is just 0. So let me just write that out. So first, in each call, y is divided by 2. So we have that the floor of y over 2 has 1 fewer bit than y. And that then implies that there are n recursive calls. So now all we have to do, we figured out how many times our algorithm recursively calls itself. The only thing left to figure is how much computation do you do in each recursive call to multiply? And then we just add it up over n times and we find the result. So in each call, in each recursive call, we do the following operations. 1, we do a division by 2, which is floored. And so that's just the bit shift, a right shift. We do a multiplication by 2, which again is just a bit shift. Multiplied by 2, which is just a left shift. So these are both constant time operations. And then 3, we do a test for even odd. Right here, we test if is y even. To do that, you can just look at the last bit, right? And see if it's a 0 or a 1. Look at last bit. And 4, we do at most 1 addition, right? We do an addition if y is odd, then we add x and 2z. And so now the only question is, we know addition, if we have 2 n-bit numbers, then addition is big O of n. And so the only question is, how big can the numbers that we're adding be? Each time we're adding x and then we're adding 2z. This 2z is going to approach it's going to be smaller than x times y, because in the end result, we're just going to output x times y. And so the question we're kind of asking is how big, if x and y are both n-bit integers, n-bit numbers, how big can x times y be? Maybe think about that for a second. It can be at most 2 n bits, right? So z can have at most 2n bits. And so you're adding an n-bit number and a number that's at most 2n bits. And so this operation is big O of n. And since we do this n recursive calls, and each one we have to do an addition, which is big O of n, the overall algorithm runs in big O of n squared time. Now, why 2n bits? Well, maybe I convince you in one way, is that what's the biggest number you can represent in n bits? It's 2 to the power of n, right? Or it's actually 2 to the power of n minus 1. What's 2 to the power of n multiplying 2 to the power of n, right? That would be the biggest product you could calculate by multiplying 2 n-bit numbers. 2 to the power of n multiplying 2 to the power of n is just equal to 2 to the power of 2n, right? Which then is a 2-bit number, or sorry, 2n-bit number. So in actuality, I can only encode 2 to the n minus 1, right, with a n-bit number. And so 2 to the power of n minus 1 multiplying 2 to the power of n minus 1 is smaller than 2 to the power of 2n minus 1. So it'll take at most 2 n bits to record the product of 2 n-bit numbers. Now, it's kind of a cool algorithm. It's simple. It takes only a few lines of code to implement, and it runs in n squared time. You can ask, can we do better? And as I kind of mentioned before, we should always ask that question. And in this case, the answer is yes, we can do better than this. This is good enough for this chapter, but it turns out we'll do better 2 times. We'll first improve it with a first divide and conquer algorithm, and then we'll introduce actually the fast Fourier transform, and we'll come up with an even better algorithm for this. So you'll have to continue through these lectures, and we'll see better ways to do this. The next problem, so we've done now addition and we've done multiplication. Addition is big O n, multiplication is big O n squared. Division is, I'm not going to go through the algorithm for it, but what do we mean when we have 2 n-bit numbers and we want to perform division? Well, if you're given an x and a y that's not 0, and you want to compute x divided by y, then what you're trying to do is find the quotient and the remainder, right? The quotient is how many times does y go into x, and r is what's left over, right? And so you can always then write x as q copies of y plus the remainder r, where the remainder is smaller than y. There's also an order n squared recursive algorithm for computing q and r, which then is what we need to perform division. It's similar to the multiplication algorithm. Take a look at the textbook in this chapter to read more about it, but we won't actually go through it in this course. We don't need it. You can just know that it exists. Okay. Now I want to get into modular arithmetic. So I think, as most of you would know, this is talking about the operation x modulo n, something like that. And so it's really, you can think of it as a system for dealing with a restricted set of integers. So when we're doing calculations modulo n, the result will always be a number between 0 and n minus 1. Right, so x modulo n is the remainder when x is divided by n. So given integers x and n, we can write x as the quotient times n plus the remainder, right? That's what, just divide x by n. It goes in q times with a remainder of r. And then x mod n is just the remainder. So x mod n is the remainder when you perform division of x divided by n. That's what modulo means. And so the remainder is always going to be a number, an integer that lies between 0 up to, but not including n. And so we can really think of, in this notation, we can think of modulo, as a function, right? It takes in x and it takes in n, and it outputs the remainder r. There's another notation that you'll commonly see when we talk about modulo, or modular arithmetic, and that's the two numbers being congruent. And so we say two numbers are congruent or equivalent if they have the same remainder when divided by n. In this case, we write x, and then we write this equals sign with 3 horizontal bars, which is kind of the equivalent sign. So equivalent sign. We write x is equivalent to y, and then this is in parentheses. So here, notice here, not in parentheses. So when we write x mod n, think of that as a function. It actually outputs something new, which is r. When instead we write x is equivalent to y, and then in parentheses mod n, we're just saying that these two numbers, whatever they are, they don't have to be mod n numbers. Like, they are equivalent. They have the same remainder if I were to divide them by n. But it doesn't modify x and y in any way. It's not a function. It just is a statement about those two numbers. So states that two numbers have the same remainder. So x is equivalent to y modulo n is the same statement. So this means if and only if. If and only if n divides x minus y with no remainder. Anytime I say something divides something else, I mean that the remainder is 0, right? It goes in perfectly. So let me establish that result. This will turn out to be useful for us. So if x is equivalent to y mod n, that means they have the same remainder, right? So then there, when I divide by capital N, so then there exists two numbers, P and Q, and an R that are all natural numbers, such that X can be written as P copies of N plus a remainder R, and Y can be written as Q copies of N plus the same remainder, where the remainder is less than N. And notice, just to emphasize, same remainder. Same remainder R for both. Right? That's the definition of equivalence. So now let's just subtract these two, right? Then I get on the left-hand side, I get x minus y is equal to p minus q copies of n. And then the r's cancel out because I don't know if I just said divide. I meant to say subtract. I'm not sure what I said, but subtract the first and second, like the second statement from the first. And then you see, right, that x minus y is just this integer number of copies of n. And so n divides x minus y. N goes into x minus y exactly p minus q times. Right, and so that proves the result. We see that these two statements are equivalent. X equivalent to y mod n is equivalent to x minus y equals some integer number of n's. Let me give you an example of this. So so 19 mod 9. So this is what's the remainder after I divide 19 by 9? Well, 19 goes, or sorry, yeah, divide 19 by 9. So 9 goes in 2 times, right? That makes 18, and then you have a remainder of 1. So this is going to be equal to 1. And you also notice that another thing I could say is 19 is equivalent to 28 mod 9. Right? These are not numbers between 0 and 8. They're not, they haven't, but they both have the same remainder when I divide by 9. Because similarly, if I divide 28 by 9, it goes in 3 times with a remainder of 1. And then you can see from above, if we go 28, 28, having trouble writing an 8. 8 minus 19 equals 9, which is divisible by 9. Right? And that's this statement here. N divides x minus y. Here, x minus y is 28 minus 19, and x divides it. It goes in exactly 1 time in this case. Okay. Let me give you one more rule, and then we'll end this lecture. So substitution rule. So if I have 2 numbers, x is equivalent to x prime mod n, and y is equivalent to y prime mod n, then x plus y is equivalent to x prime plus y prime mod n. And also x times y is equivalent to x prime times y prime mod n. So let's take these 2 examples. X is 8, x prime is 2, y is 10, y prime is 1, and n is 3. So we can see from this that x here is equivalent to x prime mod n, and also y is equivalent to y prime mod n. And we also have that x plus y, which is 8 plus 10, that's 18, is equivalent to x prime plus y prime. So x prime is 2, y prime is 1, is equivalent to x prime plus y prime, which equals 3 modulo 3. Right, they're each divisible by 3, and so they have a remainder of 0 when I divide by 3. Also, x times y, which is 80, is equivalent to x prime times y prime, x prime times y prime, which equals 2 modulo 3. They both have a remainder of 2 in this case. And one cool thing is that I can actually use this result and apply it multiple times to simplify some modular expressions. So an example is if I want to compute 4 cubed mod 3, I know that 4 is equivalent to 1 mod 3. And so 4 to the power of 3 mod 3 is equal to 4, just take modulo 3 inside, 4 mod 3 to the power of 3 mod 3, which is equal to 1 cubed, right? 4 mod 3 is just 1. So that's 1 cubed mod 3, which is equal to 1. And this is kind of useful because I didn't actually have to compute 4 cubed to be able to compute 4 cubed mod 3. Now, if you're not sure what happens here, basically what I did is 4 cubed is just like 4 times 4 times 4. So I just applied this multiplication rule 2 times. In the homework, you'll actually do exactly this as well, just to work it out for yourself. But let me show you a more interesting one. So here is a number that's absolutely enormous, 2 to the power of 2 to the power of 2006. You could never calculate it and then take mod 3. But we don't have to, because we know the result is either a 0, a 1, or a 2. Those are the only options when you're taking modulo 3. And so we can use this same trick to simplify this. And so what I can do is go, well, 2 to the power of 2 to the power of 2 to the power of 2006 is equal to 2 multiplying, or sorry, 2 times 2, or 2 to the power of 2 times 2 to the power of 2005, right? I just brought 1 2 out of this 2 to the power of 2006. And this is equal to 4 times, or to the power of 2 to the power of 2005. And so I get then that 2 to the power of all of that mod 3 is equal to 4 mod 3 all to the power of 2 to the power of 2005. But we know that 4 mod 3 is just 1, right? 3 goes into 4 once with a remainder of 1. And so this is just equal to, and I should write another, sorry, mod 3 outside of here, because the result of this, we don't yet know, is a number less than 3. So this is just equal to then 1 all to the power of 2 to the power of 2005 mod 3, which is equal to 1. And so I was able to calculate this, the mod of this enormous number, without having to actually calculate the number. And that can be quite useful. All right, last things I want to mention in this lecture. I feel this has gone slightly long, but that's okay. So modular arithmetic also satisfies the usual properties of addition and multiplication. So there's associativity, which is that I can either add x to the result of y plus z, or I can add x plus y and then z, and it doesn't change it. Commutativity, which is that x multiplied y is the same as y multiplied x. And distributivity, which is that I can go x multiplying y plus z, and that's equivalent to x multiplying y plus y multiplying z. And the final thing is that I can do addition, multiplication, and division all as modulo n operations. So if I have 2 numbers, x and y, that are between 0 and n, since each number is less than n, its number of bits is some lowercase n, which is smaller than log base 2 of n, right? Because it takes only log n bits to represent the number n, capital N. So then modulo addition in this case is an order n operation where n is the number of bits needed to encode these numbers. And I just use the regular addition algorithm, and then I subtract off n if the result is bigger than n, because the result can be at most 2 times capital N. Modulo multiplication is an order n squared operation where I use the multiply algorithm to get a number. That can be, though, that's going to be too big in general, like it won't be a mod n number. And so then I do modular division, or sorry, then I do run my regular division algorithm afterward and find the remainder. So I run the multiply algorithm, and then I run the division algorithm to divide by n and find the remainder r. And that's the result of modulo multiplication. Modulo division, this one we need a little bit more thought, because the thing is that if I just try to compute x divided by y, the result of that might not be an integer in 0 to n minus 1. And so this is what we'll get to next lecture. But I want to stop there, and thanks for watching, tuning in, and I'll see you in the next lecture very soon. Okay, bye everyone.